This is chapter 8, and I've called it a very important chapter. It talks about bonding, and it's chemical bonding. I know we've talked about ionic materials, but there's also covalent bonds with molecular materials. Very, very important. For those of you that enjoy conceptual thinking, this is your chapter, okay? What do I have here? Well, why do I call it important? Here we have some DNA. Normally it rotates if I'm giving this in the class. It's not doing it here. This is something that is biological, so that has a huge importance. On the bottom, if you look around the room where you're sitting, there's many manufactured items. There may be wooden chairs. You know, there's all sorts of things. So these are things that we use every day. Okay, I guess I'll call it that. What I have here is ethylene. We'll be talking about that in chapters 8 and 9. And it can undergo a process called polymerization. And what it makes is polyethylene, your milk jugs and your bags. All of the bonds here are covalent bonds. And that's what this chapter is about, teaching you what they are. So as we begin, I'll draw your attention to the things here on the bottom. By the time you finish chapter 9, you will be able to draw a Lewis structure. You'll be able to do VSEPR. You'll be able to tell the electron domain geometry. You'll be able to tell the molecular geometry. We don't give you any crutches for this. Everything has to be learned. But what it is you're going to learn why things have the formulas they have. Remember, you had to memorize nitrate ion. Well, this chapter is going to show you why that ion has that formula. Sitting up on the top are three very distinct types of substances. I'm hoping when you look at the first, you say, I recognize it as ionic. I'm hoping as you look at the second, you say, I recognize that as molecular. And I'm hoping when you look at the third, you say, those are elements on the periodic table, those are metals. So what we're going to be teaching, well, we've already talked a bit about ionic bonding. I don't know if we go any deeper, but molecular bonding is the next two chapters. And again, DNA, things around you, all sorts of things have covalent bonding, molecular bonding. And in chapter 12, we'll talk about how the metals undergo bonding. So that's the essence of 1210. It's teaching you about bonding, but in order to do that, we had to have all that prep from the other chapters. Again, assigned homework problems. I hope that you do them. It is your choice. My hope is if you've been doing them, you're earning the grade you desire. If you're not earning that grade and you are doing them, we do need to talk because there might have to be, no, there should be a change in how you go about studying. Again, a hard discussion, but a necessary one. So you're going to kind of flip over when I say this. I'm going to say that there is not a sharp boundary between ionic and covalent bonding. Any science that you study, the deeper you go into learning, you see how things start to change. We are chemistry 1210. So for us, it's extremely convenient to consider those two extremes separately, okay? We will say, if I have a purely ionic bond, it is a simple electrostatic model. What do we mean by that? We mean the positive and negative charges on the ions. But it's going to be needed to be modified. I'd be lying if I told you that's all there is, because there are many solids that have alternative theories. They are not for this course, but I have to say that they exist. So if we're going to now talk about covalent bonding, why does it happen? It's because ionic bonding is not energetically favorable. And I want to show you this picture because this picture represents all three types of bonding. We have water in the container, and that would be covalent because water is a molecule. We have a spoon, which is a metal, and that'll have metallic bonding. And then let's just say this white substance is sodium chloride, and it has ionic bonding. So I'm not doing any deep example. I'm saying let's put some salt into some water. That's how simple this really is. So there are again these three major types. The ionic, and that's down here. And you know, as I'm reading that book about memorizing things, they said an image. I realized the last one we had was the lattice, and it had all the different pieces. So for whatever reason, your book author said, let's call ionic with the positive and the negative charge. Contrast that to the covalent. We do not see any charges when we have a covalent bond. We are learning in this chapter the electrons are shared, and the visual of it is a very, very, very different representation. Finally, in chapter 12, we'll talk about metallic bonding, and it'll also have a lattice, but every lattice point will be an atom, and that's where the electrons are going to be delocalized. So notice, ionic, we have an attraction, and it is electrostatic. In covalent, we have sharing of the electrons, and in metallic, we have delocalization. That's the insight. That's the big picture we're also trying to teach as we teach the details. So you already know this is S territory. This is P territory. This is D territory. We've already done that in the earlier chapters. Now we're going to use that as we talk about Lewis symbols. That is the first section in our chapter, and that refers to the electrons in the outermost shell. So whatever n value is the outermost shell, the quantum number, those are the ones that are going to be involved in bonding. So again, you know what n is. You know what quantum numbers are. You've got the background now to understand it. The valence electrons, because we're 1210, they're really going to be the S and the P. And use your periodic table. I've encouraged you all semester right all over the thing. So all the facts that you need are there. So what is a Lewis symbol? Well, it's the chemical symbol from the table plus the valence electrons. I normally write it across the blackboard. I step away. I ask for questions. Nobody can respond here, so I really have to change my style. If I take the element lithium, there is its chemical symbol. And it is a 2s1. It has one electron. I will represent that by this dot, all right? Let me go all the way down to oxygen, which is further down. It is a 2s2, 2p4, for a total of 6 electrons. The questions people are going to ask me is, how do I put them? Well, 1, 2, 3, 4. I have a total of 6, 5, 6. It doesn't matter where you put them. You can only have a maximum number of 2. All right, so that's the first thing. What I want to draw your attention to is look at the correlation between oxygen and sulfur. Sulfur has a 3s2, 3p6 for a total of 6 electrons. So as I write the symbol for sulfur, 1, 2, 3, 4. Here I'm going to go 5 and 6. Those are the Lewis symbols. Those are the Lewis structures. Notice these are all from the row with n equals 2. Notice these are all from the row n equals 3. And again, it normally involves most likely the s and p electrons. As I was doing this, I noticed I do have some mistakes. So this is what I'm going to do to everything that I wrote here, okay? I am going to draw them from scratch, which may be more informative. Remember, I'm only using the valence electrons. They come from the n shell that is the highest number, all right? We don't really have too much to decide if we have carbon. Carbon is an S2P2, for 4 electrons. I put my carbon down, 1, 2, 3, 4. That is my Lewis symbol for carbon. For aluminum, I have 3s2, 3p1. I have 3 electrons. There is my Al, 1, 2, 3. Put them wherever you want, but you can just put one around each aluminum. Now, when I look at bromine, what's going to happen? You see, this was our filling order, but we really should have rewritten it as 3d10, 4s2, 4p5. Now, when I look at the electrons in the highest level, I have 7 electrons. 2 plus 5 is 7. And what I will do is I'll put the symbol for bromine. I'll go 1, 2, 3, 4, 5, 6, 7. It doesn't really matter where you put them, but bromine should have 7 electrons around it. And for cesium, I guess I could have left that. It has a xenon core, and in its valence shell, where it's n equals 6, it has only 1 electron. So I actually could have just left that as it stood. Now, just like when we did stoichiometry, limiting reagents, please make sure you can do this with 2 hands tied around your back, because we're going to build on this. And if this is rocky, the next steps really don't come very smoothly, okay? So this brings to mind, as we talk about Lewis, he also had something called the Octet Rule. There's a lot of history behind it, but I don't want it to clutter what we need to accomplish. We know that atoms, they're going to gain or lose or share electrons in order to get a noble gas configuration. So here we are comparing ionic versus covalent. So far you've really dealt with ionic. When we had magnesium, it is a metal. It is on the left. It had those 2s electrons. And you know that magnesium readily loses them to form the magnesium 2 plus ion. When I have oxygen, it has the helium core. It is a non-metal, and what it has is a S2, a full shell, but then what it has is this P4. And the P4, if it could pick up 2 electrons, it could have a full shell. And that's essentially what oxygen does. It gains the electrons. So this minus 2 electrons, this is plus 2 electrons. We get the noble gas, and that's where we get our ionic material, magnesium oxide. So again, you memorized it back in chapter 2. Now you can understand where it comes from as we're moving forward. So that's all about ionic. That is truly the transfer of electrons. But what about if it's covalent? You know, I said the word sharing electrons. Well, when I look at this, I see bromine, and I'll rewrite it argon 3d10, 4s2, 4p5. There's my valence electrons, and there are 7 electrons. If I want to make a Br2, and we'll talk more about this in the next section, I would go 1, 2, 3, 4, 5, 6, 7. There's my 1 bromine. 1, 2, 3, 4, 5, 6, 7. There's my other bromine. Notice these 2 electrons are shared in between the 2 bromines. So this chapter section is here to teach you how to write a Lewis symbol. Next section is take those Lewis symbols, start to build, I don't know, just a 2-atom bond, but then we're going to move on to the bigger molecules.